Hello everybody, I'm going to do a little video now about energy changes in chemical reactions. I've had a nice bit of feedback from some of you about this work. Some of you found it okay. Quite a lot of you found it okay. Some of you found it really enjoyable, which is nice. I'm just going to start off then. So, typical with me, I haven't actually prepared anything. I'm just going to work through my thoughts on energy changes in chemical reactions. And what I want to show you is the fact that it's, by me just talking about it and getting through the content just off the top of my head, I hope you're going to realise that it's not actually that tricky. It's a nice topic and it sort of makes sense. Okay, first thing I'm going to start off with is just putting some basic ideas about chemical reactions. Alright, so if this is a reaction, that arrow in chemistry means turns into, and we start off with chemical reactions, we start off with things that are going to react together, and they're called the reactants, and they turn into products in a chemical reaction. You produce products. So reactants in chemistry turn into products. Now, sometimes when a chemical reaction happens, when reactants turn into products, heat is given out. So heat is given out. Or sometimes heat is taken in. Okay, so the way you might think about that is sometimes chemical reactions, for you, they will feel hot, and sometimes chemical reactions will feel cold to the touch. And these two types of chemical reactions have got different names, and I know you've been studying it this week, and they're known as exothermic and endothermic reactions. So in this little video, what we're going to be talking about is the difference between exothermic reactions and endothermic reactions. We'll then move on to bond breaking and bond making, and then finally on to calculations on bond enthalpies, or bond energies, sorry, I went a bit A-level on you there, bond energies. Alright then, so first thing I'm going to look at is exothermic and endothermic. So I'm going to draw what are known as two reaction profiles here, so I'm just going to focus a little bit. Exothermic and endothermic. Alright then, so I think endothermic, I'll write them out full because I haven't written them anywhere else, and exothermic. I'm sure you've realised this and you've read it on different websites. The suffix there, thermic, is to do with energy or heat energy, so it's like thermal underwear, keeps in your heat. Anything thermal is to do with thermal energy, like in physics. And exo, it's the same sort of root of a word like exit. So thermal energy exits, thermal energy leaves. All right. Whereas endothermic, so this is to do with thermal energy or heat. So this bit is heat. So exothermic meant exit heat or heat exit, and endothermic, endo means inside or comes in. Place you might have heard of this. We have an endoskeleton, so we have a skeleton inside our body, whereas crabs and crustaceans, they have an exoskeleton, which is an external skeleton. So endo is to do with, now this is not, this is the way I remember it, endo sounds a little bit like Indo. It takes heat, Indo, doesn't it though? Yes, it does though. You got to go with me on that. It really works. So, Indo. Maybe write dough like that. I don't know how to spell Indo. It takes it Indo. Doesn't it though? Yeah, it does though. Okay, so you've got two types of reactions. You've got one where heat exits and one is taken in, where heat is taken in. So, what you have to do is then, I'm going to just draw a little beaker to represent a chemical reaction maybe happening in a beaker. So if you had an exothermic reaction and they had one of your reactants in the beaker and you put another reactant in, what you would see in an exothermic reaction is the heat in the reaction would leave. Heat would exit. So if you had your hands around this beaker, you would feel heat leaving. So the chemicals themselves are losing heat, but because they're losing heat, they're warming up the surroundings. So if everybody in our lab had a little beaker with an exothermic reaction going on, the room would get warm. What you have to know though is, so you have to know that exothermic reactions get hot. Can you see the colour system I've used there? Exothermic reactions release heat. And this is something called an energy profile. And what it means is, what you do is you write a line which represents the energy, which is sort of the thermal energy in this case, of the reactants. So the reactants in any chemical reaction have a set amount of energy, and in an exothermic reaction, what they do, the reactants lose energy to the surroundings. So if something loses energy at the end of the reaction when its products, if you have a look at this, the products have got a lower energy than the reactants. So energy has been lost. Now this is sometimes known as delta H, or we can write it as energy change, or I went a little bit, or it can be known as enthalpy change. But yeah, you'll see all of these things in your notes. So delta H, and it can be energy change. It can also be known as enthalpy change, which is a bit more A level. But you'll see it in some of these questions. Enthalpy or energy change. So just to make this clear then, if the reactants are losing energy, you've got to think, where does that energy go? The energy goes into the room, so the room gets hot, or the thermometer gets hot, or whatever it might be. But the chemicals themselves inside have actually lost energy, but they've lost energy to you. Alright, so the converse argument is an endothermic reaction, where you start off with some products. Oh no, you don't. You start off with some reactants. Careful, Norton. You start off with some reactants which have got a set amount of energy. So here's the reactants. Let's put the other reactants in. You mix them up. But for this reaction to happen, the products have got a higher energy than the reactants. So to make this reaction happen, you've got to give the reactants energy. So what these types of reactions do is they take energy from the surroundings. They take energy in though. So if you think, well, why does that make it feel cold? Well, if you had a load of beakers like this in the room, where you've got the reactants mixed together and they all need to take some energy in, they would take the energy from the room and the room would start to get colder. If you put your hands around this beaker, the reactants would take this amount of energy from you, this delta H here, and your hands would feel cold because the chemicals are taking energy from you. So they take energy, heat energy in though. So the energy of the chemicals actually goes up, but you feel it as getting colder because it's taking energy from you, from the surroundings. So the way that the examiner wants you to talk about this is an endothermic reaction takes energy from the surroundings. From the surroundings. The surroundings bit's really important. And an exothermic reaction releases energy to the surroundings. And I would just want you to think, if you ever get stuck on that and go, what does that mean in terms of heat? Imagine your hands are surrounding the beaker and something is releasing energy, this one, exiting energy, you would feel it get hot. So pretend your hands are the surroundings and then you can work out if it's going to get hot or cold. If something is taking energy from the surroundings, okay, the surroundings are my hand, it's taking energy from your hand, it's going to feel cold. So, you were asked to do... So some of you, I hope most of you are just sitting there going, yeah, that wasn't hard. You know this. There might have been some useful stuff in there. So you had this sheet at home, didn't you? Where you look at this and they might ask you an exam, is this exothermic or endothermic? Well, you've got energy at the start and the energy at the end is lower, so energy has exited, so that is exothermic. And it's exothermic. The energy change has gone down. You'll find later on that the energy change, it says here, if the energy change has gone down, the sign of the energy change has to be negative. All right? So when you work out this gap, so this gap is 76, we show that it's an exothermic reaction by putting a negative sign in front of the number. All right? And we'll see the other side here, but it says... that should be an H. Heat energy turns into chemical energy. Okay, so it takes in heat energy, which makes the chemical reaction happen. The products have less chemical energy than the reactants. Okay, it gets hotter because the heat goes into the surroundings. You didn't have to write that, but I've just added that on now. And the sign is negative because the energy has gone down. The energy of the chemicals has gone down, and we use a sign to show the direction of that energy change. Here's endothermic. So the reactants, the products are higher up, so you have to put energy in to get from the reactants to the product. So they take energy in from the surroundings. Just like if you've got a ball and you want to lift it up onto a higher shelf, you have to put energy in to lift it up onto the higher shelf. Whereas if you have a ball on a higher shelf, when it falls down to the lower shelf, it actually releases energy. So it loses energy, gravitational potential energy. So it's very similar to sort of physics ideas that you've got. And just out of interest, which one do you think is the most common? What type of reaction is most common? Exo or endo? You might have read it somewhere, I don't know. It's exo. Exothermic reactions are by far the more common type of reactions. It's not quite like this, but it's more likely. It's easier for something to lose energy. Most chemical processes, most physical processes, like to lose energy to get more stable. In an endothermic reaction, you have to put energy in. It's just less common. So just out of interest, exothermic reactions are more common. You'll more commonly see exothermic reactions in the lab. And yeah, so products have more chemical energy than reactants, so the energy change is going up, and we represent that with a positive sign with any number it might be. When we do calculations later, you have to put a positive sign in front of any number. And they get colder because they take heat in from the surroundings. So if the surroundings were your hand would feel cold. Right, you've then got these other bits, which you might think at first glance didn't seem that important. But, so hang on, I've got the answers somewhere to this. Come on, Norm, what have I done with them? Which is the example reactions. Now, I haven't got my sheet there. Have I got it underneath? No. Now, you need to know some example reactions, and I'm a little bit stuck here because I can't find my room's a mess. It's just full of kids' stuff everywhere. Right, so example reactions. So if you're asking it, you could be asking an exam for example reactions. So I'm going to put the exam in example. Didn't need to say that. Wasn't funny. Right. Reactions that get hot. Well, combustion is an example of a reaction that gets hot. So the combustion means burning, but I'd like you to use the word combustion. What other ones were there? Neutralization is an example of a reaction that gets hot, so an exothermic reaction. There's others. All right, I can't remember my list, but when you've done the research on this and when you've looked at the answers, there's a few that you needed to put in. Endothermic reactions, they're a little bit specific. There's one called thermal decomposition. Now, the very word thermal decomposition means to break down, and thermal means using heat. So you have to put heat in dough to make something break down. So this is where you actually have to heat something up with a Bunsen burner to get the reactants to turn into the products. So thermal decomposition reactions. And I think there's one that you have to know. I think it might be on the back here. There's thermal decomposition. Metals with acid, if they get hot, you might remember putting metals in acid. They just get hot. They give out heat. This one, reaction of an acid with sodium hydrogen carbonate. They get cold. So you'll have seen that when you look through the mark scheme. Sodium hydrogen carbonate with acid gets cold. Uses in everyday life. Heat packs, fires, keep you warm. Car engines, that's got combustion going on. Endothermic reactions, I think you might have had cold packs, ice packs. And not the type that you put in the freezer, so chemical ice packs. And again, there were some other examples, but... Alright. I'm going to talk now about this other little bit on here called activation energy. So I know this is a bit waffly, but I'm not going to re-record this video. You're just going to have to deal with me chatting on and being a bit disorganised. Okay, so firstly, if I just draw an energy profile and I do it like that, alright, well firstly, have I just drawn an exothermic or an endothermic? These are the reactants, these are the products. Is that exo or endo? Alright, here's your answer coming up. Spoiler alert. Right, so the energy is high at the start and it's lower at the end, so that means energy has exited. So it's going to have a negative sign and it's exothermic. So in this exothermic reaction, energy is lost. Now, what you have to do with most chemical reactions, there is an energy barrier that stops a chemical reaction from happening. Now, before I just draw it on and call it the activation energy, which you'll have read about, I want you to imagine that you've got a match. This is going to be a match. Check this out for art. All right, if you've got a match and you've got that out of a matchbox, you know that when this match starts burning, it will definitely release energy to the surroundings. In other words, it will get a flame on it. But you also know, knowing a little bit about matches, that matches don't just spontaneously burst into flames. So even though they can give out tons and tons of heat, they don't. They're safe. They are safe until you do something with them. And what that thing is that you do is you strike that match against the edge of a box. Now, when you strike that match against the edge of the box, you give it a little bit of friction. That friction provides a little bit of heat, and that gives it enough energy to start off the reaction. So in other words, with most chemical reactions, there is an energy barrier. And hopefully you can see that in the case of a match, that's quite an important thing to have. So this energy barrier is drawn like this. This represents an energy barrier between reactants and products. So to get to reactants and products, yes, overall you will lose this amount of energy. But to do that, you have to give the reactants enough energy to get them to the top of this hill so they can roll down the other side. So you need to put in a little bit of energy so they can roll down the other side. Now overall, you say, what's the difference between the reactants and the products? Well, that's that side and that side. And this hill, from where the reactants are to the top of this hill on this reaction profile, is known as the activation energy. Other examples of activation energy, a firework. You know that a firework is effectively a bomb that's ready to give out loads and loads of heat. But it's not just going to explode on its own. What you've got to do is you've got to actually light a fuse which will generate enough heat to give it a little bit of energy, and once it gets that little bit of energy, it will release all of its energy. So activation energy is an energy barrier, and the way that we say that in the exam is it's the minimum amount of energy required for a reaction to happen. So activation energies can be large, activation energies can be small. What you need to be able to do is to draw and label the activation energy, and it goes from the reactants to the top of this bump. Another way just to think about it, if it helps, is if you're on a little walk here, if you're on a walk and you're halfway up a mountain on the edge, on a ledge, and there's a big mountain in the way, and there's your campsite at night, and you want to get to your campsite, right, you know that you're at a certain level, like 1,000 feet, and your campsite is at 500 feet. So yes, you've only got to drop down 500 feet, but there's a mountain in the way. Oh, that's a bit of a shame. So even though there's only a 500-foot difference in height, you've still actually got to climb up the mountain before you can get down the other side. All right? So you might have to climb another 700 feet here and then go down another 700 feet here. But so overall, you've only dropped minus 500 feet, but you still have to climb that mountain to get to your campsite. And that's the equivalent of the activation energy. If you only put in 600 kilojoules of energy, you're only going to get back to here and then slide back down to your ledge. You're never going to make it to your campsite. But if you put in just enough energy to get you to the top, well, I don't know, you can slide on your bottom all the way down to your campsite if you like, because you've made it. All right, if you don't provide enough energy to get over the activation energy, you're not getting to the other side. It's late at night here, and I'm already thinking, God, am I just over-explaining this? And there'll be some of you going, yes, sir, you really are. Okay, so now I'm going to draw an endothermic reaction. How did I know that it's endothermic? Because if this is energy, the products have got more energy than the reactants. So if you were a reactant, you had to put energy in dough. So you had to increase the energy. It's going to be a positive sign. But even endothermic reactions have an activation energy that you have to get over. And you just draw it on like that. You draw a loop. All right. And the activation energy is drawn from the reactant line to the product line. So again, there's a little analogy. You're out camping with D of E. There's your campsite. You're at 500 feet and your campsite's at 1,000 feet. You only need to do, in total, 500 feet of climbing, but there's a mountain in the way. So what you actually have to do is you have to climb all the way up here. Let's call this, you have to climb to 1,500 before you can slide down on your bum on the other side. All right? So even though you will only gain 500 feet in total, you have to climb over the mountain first. And guess what? If you don't put in enough energy, you're coming straight back down that way. But if you do put in enough energy, the reaction just carries on and it slides down the other side. All right? So the activation energy is the minimum amount of energy required for a reaction to take place or for a reaction to occur. You can think of it as an energy barrier that's stopping the reactants turning into the products. I think I've done a good job on this, and I'm not gonna go back and watch the video. So if I've made a hash of that, you're just gonna have to let me know. All right then. So if the examiner does a diagram like this and says, right, is that exothermic or endothermic? You would say exothermic. Then they might ask you to label the activation energy. So you'd have to be, sorry, that's endothermic. Endothermic. I take it back. It's endothermic. Activation energy would be from here to here. Common mistake is to do it from the smallest side to the top. It's not that. So I would write activation energy or EA or whatever they wanted you to write. They'd ask you what is the enthalpy change, and that's the difference between the reactants and the products, or they might call it the energy change. That's delta H there, and that's what you have to label. Those sort of things. They might then say, give an example of one of these types of reactions, and you would say thermal decomposition, maybe, or you would say sodium hydrogen carbonate and acid. And that's how they can ask questions in the exam about exothermic and endothermic. All right. I think I'm going to leave that as video number 1. Maybe I am. Introduction to exo and endo. Maybe not, actually. I haven't got the answers to these, so you know what? I should be good enough at chemistry to not need the answers to these. They look alright. Alright, let's have a little look at these then. This table shows the temperature changes in some reactions, so you should have all had a little look at this. I'll ruin my pen. Oh dear. Right, a reaction A starts at 21 and ends up at 65, it's released energy. Alright? If the temperature increases, that means the chemicals were releasing energy to the surroundings. Exothermic, endo, it's got hot, exo. Some people at this point ask me, are there any reactions out there that are neither exo nor endo? In other words, where the reactants and products are exactly the same energy. And every year I go, well, I know there's some that it's very, very close, like plus or minus 1 or 2. So yeah, probably there's plenty of chemical reactions out there when you do the chemical reaction and you don't really notice a massive energy change. Look what I've just done. Snapped my pen. I wasn't even being angry. The cheap junk. It's my daughter's though. She's gonna go mad. Right. For each of the reactions shown, draw the reaction profile. All right, draw an arrow to show the energy. I like these questions. I think they're quite clever. Draw an arrow to show the overall energy change and label this as E, but in the exam you might be asked to label it as delta H. Draw an arrow to show the activation energy. Okay, so this one, CH4 plus H2O, methane and water makes carbon dioxide plus hydrogen, and it's a positive enthalpy change. So that means energy change is going up, it's positive. So I'm just going to put my other line up there. I'm going to go reactants and products. I'd write them out in full in an exam. But it's gone up, so it's gone up by 208. I'm happy with that. To chick, was that a word? I don't know. And then that's the overall energy change, plus 208. May as well put in the units, kilojoules per mole, that's called. At A level, we write it like this, kilojoules mole to the -1, but kilojoules per mole. But if I accidentally do that, it's just an A level variation instead of putting the slash in there. All right, activation energy goes up like that, and the activation energy, oh, I've sort of put that arrow in the place where I went. That one is A. Let's label this E, label this A. Next one, energy goes down by 76, so I'll draw it down there, I'll do a loop on there. That's the energy change, I'm going to label that E. In an exam it might be delta H. It's -76 kilojoules per mole. Reactants, products, activation energy is to the very top of that. Now, in exams, right, listen to this. If you do that and you think, oh, I'm dead good at this, and you just put an arrow and do that activation energy, the examiner will mark that wrong because you haven't drawn that arrow right the way to the top. You have to draw it right the way to the top. All right? You're also not allowed to just do, if it says label the activation energy, you're not allowed to do that is the activation energy. It's not. The activation energy is from here to there. So it's this activation energy. All right. Anyway, see, this is the stuff you get in lessons, isn't it? But I'm trying to just remember all this information. You know, I will learn one day to plan these little sessions, but I'm enjoying freestyling. I like taking risks. Okay, state whether each of these reactions is exo. Burning, exo. Hydrochloric acid with sodium hydrogen carbonate, endo. Now you might have looked at these and go, how am I meant to know that? Well, you've got to, because look in your revision guides, there's a list of ones that you need to know. Acid and alkali, that's an acid, that's an alkali, so that's neutralization, and that is exothermic, always. Sulfuric acid with magnesium, if you ever put magnesium in sulfuric acid, you'll know it gets hot, exo. Ammonium chloride dissolving in water in an ice pack. Now, you might not have known that, and you might have Googled it. It's endothermic. Well, it's an ice pack. We're talking here about the ice packs that you click a little disc inside them, and they go hard, so it's a chemical reaction that causes it to go cold, that takes energy from the surroundings, rather than an ice pack that is basically just a liquid that you've frozen, and then you can put it back in a freezer. So chemical ice packs are really useful when you haven't got a freezer nearby. So for example, if you're playing football in the middle of a big field and there's loads of pitches, and if you injure yourself, you get a chemical ice pack out and put that on because you haven't got a freezer with you. All right. Thermal decomposition, you've got to put heat in to decompose. So here's your reactant, there's the product. You've got to put heat in. It must be endo. You've got to put energy indo. Electrical decomposition of sodium chloride. What? That's got to be endo as well. You know, that zapping sodium chloride with energy. Sodium chloride, I've guessed endo here. I think it is. Yeah, I'm pretty sure it is. Sodium chloride is a giant ionic lattice. MC Bockel. So if you want to decompose it, which just the decomposition just means breaking it down. If you want to break this down, do you know what you're going to have to break? You're going to have to break the many strong electrostatic attractions between oppositely charged ions in a lattice. And if you want to break that apart, you're going to have to put energy indo. There you go. It all comes back to MC Bockel. Anyway. What else have I got? What was that? Is that the same? That's the same. Cool. That's the end of the first video. Tune in next time, which is going to be in about 5 minutes for me. I'm just going to get a brew. Okay.